I'm going to briefly overview the concepts in Unit 11, Thermochemistry. First, a recap of the basic definitions: energy, heat, thermal energy, temperature. These four ideas are the core parts of this unit and topics that we've already covered in class. As a reminder, heat flows from warmer objects to cooler objects. This is a physical process where particles bump into one another, fast-moving particles speeding up slower-moving particles. The units in this, the units of energy in the thermochemistry topic are primarily joules. It's the SI unit of joules. Also present, though, are calories, calorie with a lowercase c and calorie with an uppercase c. As shown on this slide, the uppercase c calorie is the calorie associated with food. The idea today is to play upon the idea that energy can be converted from one form to another. A simple form of energy conversion that we're well acquainted with is potential to kinetic energy, as seen by this bike going down a hill. Energy conversion is a central idea that is associated with the first law of thermodynamics, or the law of conservation of energy. And this is the basic idea that energy is neither created nor destroyed. An intuitive idea, one that's often learned much earlier in science education. In order to understand energy conversion, though, we need to define two different terms: system and surroundings. The system is what we're examining. The system consists of the particles that are what's changing. The surroundings is everything else. If we're going to conduct a reaction between hydrogen and oxygen, as shown in the picture, the hydrogen and oxygen atoms themselves are the system. Everything else is considered the surroundings. The piston, the cylinder, any air that's trapped in that cylinder, the rest of the world, in fact, are considered the surroundings. Another new idea that needs to be introduced is the idea of enthalpy. Enthalpy is the energy content of a substance. It's a term exclusively used in chemistry. And in a physical or chemical process, the enthalpy of a system will change. Enthalpy is the term used in chemistry to describe the energy. So when we talk about energy, we're often interchangeably discussing the idea of enthalpy. So how do we apply that? Well, first off, there's two categories of processes. Endothermic, where heat is absorbed by a system and the change in enthalpy is positive, and exothermic, where heat is released by the system, the delta H is negative. In an endothermic process, the particles that we're talking about grab energy from the system, and often the surroundings feel colder because the surroundings have given energy to the system. The system itself, though, increases in energy, increases in enthalpy. That's why the delta H is positive. In an exothermic process, the reverse is true. The particles themselves rearrange such that they release energy. We would notice that as something heating up, and the delta H for the system would be negative. This is specifically applied to the enthalpy of a reaction. Notice that in this particular case, hydrogen and oxygen react to form water as a gas. In the circle on the left, the hydrogen and oxygen molecules are separate, and then afterwards they're rearranged to form water molecules. The energy stored in the atoms, in the hydrogen and oxygen molecules is a different amount of energy, chemical energy, enthalpy, than stored in the water molecules on the right. Therefore, the circle on the left has a different amount of energy than the circle on the right. Visually, that box on the right side of the screen shows that the hydrogen and oxygen separately have more energy the way they're put together than the water molecules after being rearranged. Therefore, the system, which is simply the atoms, lowers in energy and releases that energy to the surroundings. Notice in the pictures above, that's meant to show that if that balloon was filled with oxygen and hydrogen, notice that once this reaction occurs, it releases energy to the surroundings. We would see that release to energy in the surroundings, the exothermic, as fire in this case. So my noticing fire means that I am noticing an exothermic process because I am part of the surroundings. Another way of thinking about this enthalpy change, again with the same reaction, is that there's an energy associated with the reactants and an energy associated with the products. And notice that the reactants are above and the products are below. So if I go from the reactants to the products, the system loses that amount of energy. In turn, if I could roll the tape backwards, I would notice that to go from products to reactants, I would have to absorb the 890 kilojoules. Notice that again, we have to make sure we understand what the system is in order for this to make sense. A different visual way of looking at this is a reaction progress diagram. The graph on the left shows that the reactants are lower than the products. The x-axis in this case is time. So as time progresses, the reactants raise in energy and become products. They have to absorb energy in order to go from reactants to products. That's an endothermic process. On the right side, the reactants, as the reaction proceeds, will eventually lower and become products which have a lower amount of enthalpy. That difference in energy is the delta H, the change in enthalpy for that reaction. And so the graph on the right is exothermic. It's of interest to note, although not part of this class, that each of these graphs has an extra high bump or hill, if you will. That amount of energy is referred to as the activation energy, or the energy needed to get the reaction going. That is to say that in the previous reaction, oxygen and hydrogen react, but they don't react unless they're given some sort of jump start. And that jump start means you have to go over that hill. So a couple of final truths here about enthalpy. Delta H, the change in enthalpy, and enthalpy itself depends on the state of a substance. That is to say that water as a liquid has a different amount of enthalpy than water as a gas. Second, the change in enthalpy of a process is proportional to the mole ratio of the process. This is where we link change in enthalpy to a chemical reaction. This can be seen in these math examples. Notice that in the top reaction, nitrogen and oxygen react to form nitrogen monoxide. The delta H for that process as written is 180 kilojoules. So burning 1 mole of nitrogen, N2, the delta H is 180. But if I burn half of that amount, react half the amount of nitrogen, notice that the delta H for that is going to be 90. So the delta H for the reaction as written is reflective of the mole ratio for the balanced reaction. Notice that the third line, the decomposition of 2 moles of nitrogen monoxide, says, if I could run that reaction in reverse, the delta H for that process would just be the opposite, or negative 180. The bottom one shows something that's not a reaction. And again, make sure that we understand this is not a chemical reaction. This is just boiling water. Water going from a liquid to a gas. That's an endothermic process. The delta H for that process is positive. The liquid water requires energy to become gas water. So the amount of energy required to boil 1 mole of water delta H is 44 kilojoules. In other words, to boil 1 mole of water, 18.02 grams, I have to supply 44 kilojoules of energy to that system. Conversely, the reverse of boiling, condensation, energy is released. If I take steam and I change it into liquid water, notice that steam would release energy to the surroundings, and the steam cools, it cools down. Notice that 180 grams of water is 10 moles of water, and therefore the delta H for that process is 10 times the delta H, but negative because it's going in the opposite direction. Heat capacity is the energy required to raise the temperature of a substance by 1 degree Celsius. Notice that the specific heat capacity is different for different substances. Notice that water on that list is much higher than the other substances listed. And heat capacity, C, is related to the heat transferred, mass, and change in temperature. This is a concept we've already discussed in class. It's important to understand that specific heat capacity, specific heat, and heat capacity probably refer to the same idea, although technically in chemistry, they might have different aspects to them. In this class, we will use them interchangeably. On the right, you'll notice that water is a liquid, 1 gram at 14.5 degrees, requires an amount of energy to raise to 15.5 degrees or 1 degree. So that 4.184 joules is the heat. But because we're talking about 1 gram in 1 degree, that amount of heat, 4.184 joules, which is equivalent to 1 calorie, is also going to be the specific heat capacity. And a final note here, calorimetry. As mentioned before in class, we use a device called a calorimeter to measure heat flow. That is to say, we insulate the inside of the cup, the calorimeter, from the outside world. This means that any heat exchange is between the contents inside the calorimeter and not outside.